Okay, so hi everyone. We can start now. So basically, me and Naga Dharsan will be covering the session today. So thank you so much for 16 people who have joined till now. So we'll be recording the session. So basically, we're going to see what pipelining is. Okay, so what exactly is pipelining? Why do we need pipelining? And then there are like some hazards that happen, the types of hazards in pipelining. We'll be dealing with that. And then Nagadarshan will also be covering some questions on that, questions based on the pipelining concepts. So I'll share my screen now. Okay. So can you all see my screen? Okay.
Yeah.
Okay, so we're going to deal with what is pipelining. Okay, so essentially, how does what happens in like a program or something? You actually see. Let's just take an example of like adding two numbers. So first, you take an input, say A and B, and then you add those. You do A plus B, and then you print the answer, right? So what happens in this case? You just sequentially go with each and every step, right? So you don't jump anywhere. It's just sequential execution of steps. So I'm not like trying to just always talk in terms of programming, but pipelining essentially is in terms of improving the efficiency of your hardware in itself. So what pipelining does is, let's say instead of doing like the steps one by one, why can I not do like multiple steps at the same time? Okay, that is what we're going to try. That is the motivation behind learning what pipelining is. Okay, so pipelining, yeah, so the general overview on what pipelining is, it is widely used in modern processes. We look into what pipelining is with like a very simple example also. It improves system performance in terms of throughput. Okay, so this point we'll come back later. Okay, so we'll come back later onto what throughput is and how exactly does pipeline improve the system performance in itself. Okay, so pipelining organization requires sophisticated complication techniques such as some hardware that it requires. Okay, so what this tells is, okay, essentially in pipelining there is some amount of hardware that is required because pipeline, what do you mean by pipelining? Let me just give you a small example. Okay, so let's say you have like two instructions, say fetch and execute. Okay, so I'll just give you two options. Okay, so my option, you have to tell me which exactly is pipelining. So my option is fetch and execute, both instructions, they are different instructions, no, they're happening at the same time. That is your option A. Okay, so option B is, let's say like there's two execution steps, like two different executions, say E1 and E2 and E2 happening at the same time. What do you think is pipelining, A or B? You can drop it down in chat, or so you want me to repeat. uh, Agenda file not working, as in what is happening?
The Zoom Meet link, whether you have given us a link for something called an agenda file, that doesn't work. So if you were thinking of doing something with that, we are unable to access it. It just says file not found. The
Oh, no, no,
default
no. Just ignore that.
okay.
Okay, okay. Okay, so okay, I gave you two examples, right? So the first option is, let's say you have fetch and execute. So your fetch and execute that is happening at different same time, like your fetch and your execute stage is happening at the same time. And then your other example is where the two execution stages, E1 and E2, happening at the same time. So what do you think is the answer? Which what is pipelining? A or B? Okay, A. Nidarshana says A. Okay, so she's exactly right. Okay, so pipelining, what you're essentially dealing with, is two different instructions happening at the same time. So that is why we call it as serial processing. Okay, so everyone would, sorry. So pipelining essentially is serial processing. So what everyone would think is parallel processing. Okay, everyone would think that pipelining itself means instructions happening parallelly. So it is parallel, but it is different instructions happening parallelly. So that is essentially what serial processing means. Okay, so please don't get confused with serial and parallel processing. So in, I think even in like many websites it says it is parallel processing. So parallel processing is essentially what superscalar execution is. So your superscalar execution is what I said the second example, no? That is your parallel processing. Is it clear now? Like, is this point clear? Okay, so let's move on. So there is some amount of hardware that is required in terms of synchronization. So I said that fetch and execute, there are different instructions, but they're happening at the same time, right? So for it to happen at the same time, you need some amount of hardware that is required. So that hardware is that we will see what the exact hardware is. It's actually the buffers. We'll see why do we need them also. Okay, so that is the some amount of hardware that's required. Okay, so we'll come to the throughput point later. Okay, so what is the motivation behind learning pipelining is how do we make the execution faster? Like, how can we make something faster? Okay, so what you can use is use a faster circuit technology. So, so circuit technology so that you access things faster. So from the main memory, you should not all see main memory is something that's very slow. So you have cache, okay, and then you have your main memory.
It's
So
6:30.
uh,
I had to delay shit for you because of this, man. I had to cancel stuff for you, and then you come tell me no, we're going half an hour late. How could you?
wait.
I can.
Harish.
Oh, I'm unmuted. I'm sorry.
Yeah.
Wait.
Okay. Never mind. Okay. So faster circuit technology. Okay. So essentially, you need to make a circuit technology faster. So what do you do? That you need to try to like optimize certain processes. So accessing from the main memory is essentially a very slow process. So you need to access it from the main memory, but you can instead access it from the cache. Okay. So that's one way of like making the circuit faster in itself. Then you have to arrange the hardware so that more than one operation can be performed at the same time. This is what I said, serial processing, right? So more than one operation that can be performed at the same time, right? So this point we'll again come back to it later after we deal with like a very small example. Okay, so we'll just see the example so we can intuitively understand every point. You need not like memorize whatever is whatever. So this is like a very famous example. Okay, so okay, so this is a very famous example. So you have like four people, say A, B, C, D. Okay, so they want to actually wash their clothes. So let's say you have three units in your washing machine. Your washer unit, which takes 30 minutes, your dryer unit, which takes 40 minutes, and your folder unit, which takes 20 minutes. Okay, so this is our example, okay, that we are going to deal with now. So now let's just look at this, okay. So without pipelining, let's just say four people, the A, B, C, and D, they need to wash their clothes. What do you think they'll do? So the first person will take, so this is actually washing, drying, and then folding. Okay, the washing, drying, and the folding unit. So the first person will take 30, 40, 20. So for each of these units, so it is, which is 90 minutes. Okay, so 1.5 hours is taken by the first person. Then after the first person is completely done, the second person then goes for 30 minutes, 40 minutes, and 20 minutes. So again another 90 minutes. Then the third person, 90 minutes more. Then the fourth person, again 90 more minutes. Okay. So what happens here? So for 4%, it takes 6 hours. So 1.5 hours into 4. So it takes 6 hours for them to complete the entire process. But do you think there is a way to optimize this? Like, what can we do to like optimize this? Okay, so that is what we're going to deal with right now. So let's take just look at it over here. Let's say here is a washing unit which takes 30 minutes. So then let's say the first A person just puts their clothes into the washing unit. Then after the 30 minutes is over, it just goes to the drying unit, right? So when it's going to the drying unit, that time this washing unit is still like it's idle. It is not doing anything. So essentially, like what you can do, you can make the second person to put their clothes for washing here, while the first person is actually drying their clothes. So that is what our concept of pipelining is. So we are trying to optimize our entire process and hence reduce the time taken for doing something. So this is how our execution becomes faster. Okay, so let's look at this now. So this is where the pipelining has been done. Okay, so if you see here, so the first person is here, and then first person the washing, drying, and the folding unit. Then the second person is actually getting overlap. So there's an overlap between all of these steps. So what is happening here is they're completing their steps in 3.5 hours. So if you calculate all of this, 30, 40, 40, 40, 40, 20, these are minutes. Okay, so if you add all of these up, it sums up to 3.5 hours. Okay, so earlier what did we see? We saw it was 6 hours for 4 people. From 6 hours am I audible?
Yeah.
Okay. Can you see my screen?
No.
Okay. Till okay.
It's okay.
Till which part did you hear? Which part did you miss on? Okay, I'll just repeat whatever I said for the last 2 minutes. Okay, so this is the traditional process that we follow. So each person taking 90 minutes each for 4 people, it will become 6 hours. Okay, but if we try to pipeline it and overlap the steps so that it becomes more efficient and optimized, we are reducing it to 3.5 hours. So that is what we are doing here. So from essentially 6 hours, we are reducing it 6 hours in our traditional process. We're actually reducing it to 3.5 hours. Okay, so I'll be now explaining what these notations are. We'll be using it now soon. So this n is the number of students over here. So here we have like 4 people, A, B, C, D. So 4, and then there are the number of pipeline stages. So the pipeline stages is what there is a washing unit, drying unit, and a folding unit. There are steps or 3 stages that you need to perform in like one for one person, right? So that is k. Okay, so that the number of pipeline stages is equal to 3. So this is what we call it as latency also. So our number of pipeline stages, we call it as latency, right? So to calculate the number of clock cycles, we essentially do n plus k minus 1. So here, if you see 1, 2, 3, 4, 5, 6, 7. Okay, wait, I will show you. I think, okay, I don't have 1 second. I'll try to draw it and show. Can you see me drawing? No. Okay, so essentially what I'm telling is, so 4 is our n, so plus 3, which is our k, minus 1, so which is 6 clock cycles. So if you see, this first step takes 1 clock cycle, the second step takes 2 clock cycle, third in a third clock cycle, fourth clock cycle, fifth clock cycle, and sixth clock cycle. So it takes 6 clock cycles in total in our example over here. So now we are reducing. So we'll just now try to calculate what the speed up is. Okay, we're trying to calculate the speed up. So speed up in our first case. Okay, let's take our first case. So our speed up is essentially non-pipelining by pipelining. So you're trying to see how fast it has become. Okay, so in terms of the first case, it was actually 6 hours, right? So it took 6 hours is our non-pipelining condition. So it took 6 hours in our non-pipelining condition, but in our pipelining condition, it just took 3.5 hours. So if you take the speed up ratio, that is 6 by 3.5, it is actually 1.75. Okay, so now we will look into another condition. Okay, so 1.75 is our first speed up that we've calculated now. So how can we try to increase this 1.75? Why cannot we make it much better is our question now. So what can we essentially do? So let's take an example, the same example over here. As I said before, so the first person, they'll first put their clothes into the washing unit. Okay. So then after this 30 minutes is done, they'll actually transfer it to the drying unit, right? So while this first person is having the clothes in the drying unit, the second person puts it into their washing unit. So in the first place. So now, since the first person over here, let's say they're done with their drying unit. Okay. No, they're actually doing the drying unit. So, okay, I'm confusing you a lot. Okay, now let me tell it again. So let's say the first person is first putting into their washing unit, and then they're transferring into the drying unit after they are done with it. So the second person, they can actually put it into their washing unit, right? So now that this takes 40 minutes, even though the second person is done in just 30 minutes, they have to still wait for 10 more minutes, right? So they have to wait for 10 more minutes before sending into the drying unit. So there is some amount of delay that is there. So what can we essentially do in that case? We try to make all of the time periods of each stage equal. So instead of 30, 40, 40, and 20 and all, instead of it being different time, we're trying to make it same time. So let's say it's 30 for all. Okay. I'm just giving an example. It could be 40 for all. Okay. So let's just take a condition where it's 30 minutes for all the steps. So each of the steps that it takes, let's say it's 30 minutes. So in that case, if all of this is 30, then what will it be? What will be the sum? So in that case, it will be like actually 3 hours, no? So here 36 into 30 minutes. So it will be 3 hours. So in that case, again, we can calculate the speed up, okay? So earlier the pipelining, it was 6 hours. Now after making all of the intervals equal, it becomes 3 hours. Okay, so in that case, our speed up is 2. Okay, so so essentially what we are actually expected to do is our speed up should be proportional to the number of pipeline stages. Okay, so our speed up, which is now earlier 1.5, now we have actually optimized to 2 by actually making the intervals equal. So in that case, it becomes equal to 2. But is there a way to actually make it much more efficient, like much more actually equal to 3? 3 is the number of pipeline stages, no? So can we make it much more better is our question now. So why should it be equal to 3? That, I mean, you might ask, no? So speed up, why should it be proportional to 3, or why should it be proportional to the number of pipeline stages? So let me just, okay, so what we can do is, let's just take first the non-pipelining condition. So our non-pipelining condition. So in that case, so now how many stages do we take? So let's our k be 5. Okay, so that is our number of stages. Okay. So now in this case, how much will each? So let's take each step. All of this takes t time. So this will take. So the total time per instruction will be 5t, right? So there's a non-pipelining case. We are having 5 stages. Earlier, I mean, in our example, we had 3 stages. So now let's just set 5. Okay, now let's just take 3 itself. We had 3 stages, right? So let's say each step is taking t time. So the total time that is taken is 3t. Okay, that is fine for now, right? So for n instructions, what will be the total time? It will be n into 3t, right? That will be a total time taken. So now let's just consider it for pipelining case. So here, again, our k is still 3. Okay, so our k is still 3. But each stage, it will take t time. Okay, our k is also 3. So now I actually showed you the formula, right? So total time taken is equal to n plus k minus 1. I mean into t. Okay, so what do you do here? So it's actually n plus k minus 1 is 2. So n plus 2 into t. So what do we do for speed up? Essentially, we actually do the ratio of non-pipelining versus pipelining, right? Non-pipelining divided by pipelining condition. So if you do that, it is actually this 3 n into 3 nt by this n plus 2 by 3. Okay, this by n plus 2 by 3. Okay, n plus 2 into t. Okay. Are you all getting till here? I'm just trying to intuitively, not intuitively, but just trying to explain why you are actually considering speed up is proportional to the number of pipeline stages. Okay. So if n, okay. So if n becomes very large, okay, this t and t gets cancelled, right? So it is actually 3n by n plus 2. So it's actually 3n by n plus 2. So as n becomes larger and larger, so what will happen? So it will actually become equal to 3, right? So the total speed up will become almost equal to. So what is 3 here? That is our number of pipeline stages, right? So this is why you're telling that the speed up should be proportional to the number of pipeline stages. Okay, so is this part clear? Might sound confusing, I don't know. Anybody wants me to repeat this?
Yes.
Okay. I'll repeat it again. Okay. So in our example, what did we take? Why are you actually looking at this is because I'm just making a claim that our number of pipelining stages should be proportional to the speed up. Okay. Why so is what we are looking at now. Okay. So let's just take our non-pipelining condition. Okay, so let's keep our k to be 3. So k is the number of stages and it's 3. Okay, so now let each of these steps take t time. Okay, so now there are 3 stages. So the total instruction that is taken is 3t, right? So we always, in speed up, no, we always consider it in terms of the time taken. Okay, so that's for n instructions. The total time is n into 3t, right? This part is clear, no? Now for the pipelining case. Okay, so for pipelining, again we're taking the same condition. So each stage it takes t time, and then our k is equal to 3. So for the total time taken, we actually have this formula. No? So n plus k minus 1. And we always consider in terms of t. So we are having the t also. Total time is t. Okay, so this is number of clock cycles. So n plus k minus 1 is the number of clock cycles into t is your total time. So what is your k? It is 3. So n plus 3 minus 1, which is 2 into t, right? That is your total time. So always when you see the speed up, it is actually the non-pipelining condition versus the divided by pipeline. Okay, so that is actually n3t by n plus 2 into t, right? So this t and t gets cancelled, so it's 3n by n plus 2. So as n becomes larger and larger, our speed up will eventually become closer to 3, right? So this 3n by n plus 2, it will become closer to 3. So what is our 3 here? That's the number of pipeline stages. That is what we have kept assumed 3 to be. So that is why we are claiming that speed up should actually be proportional to the number of pipeline stages. Did you get it now?
Yeah, thank you.
Okay. So now let's just go back to this example again. So 6 by 3.5, the first case, okay, where 6 is the non-pipelining, and 3.5 we just pipelined it with all of these values being the same. So 30, 40, 40, 40, 40, 20. So that gets we got 1.75. So ideally it should be equal to 3. I mean, not equal, but closer to 3. Okay. So, but it is way far. So we tried to optimize it. What did we do for optimization? We tried to make all of the intervals same. So instead of 30, 40, 20 and all, we made all of them 30. We're just making an assumption saying all of the stages will be 30 minutes. So in that case, it will be, if you add all of this, if assuming all of this is 30, if you add them all, it's 6 into 30, which is 3 hours, right? So if you do 6 by 3, 6 hours, which is non-pipelining, by 3 hours, that is the optimized condition, then you will get 2 is your speed up now. So it is still not equal to 3. So you might ask why, right? So there's something called as loading and flushing delay. Okay, so if you can see the example, okay, here we had like our four people, right? A, B, C, D. So let's just take an example. So washing unit, drying unit, and the folding unit. Okay. So let's say the first person puts it in the washing unit. Then they go to the drying unit. So the second person puts it in the washing unit. Then the third person, okay. So they move this side, and the third person puts it in the washing unit. So essentially, it takes 3 clock cycles. So let's assume there are like each person, each step takes 1 clock cycle alone. Then it takes 3 clock cycles to actually fill the whole thing. Okay, so for the whole unit to be filled, all the washing, drying, and the folding unit, it takes 3 clock cycles. Only from the next. So next, the fourth person will go in, and then 3 and 2 will get shifted. So first person, they can just take out their clothes, right? So again, let's say we had only 4%. So now there's no more people there to put it in the washing unit. So now the second person gets their clothes out, then the third person, then the fourth person. So there are no more people just putting stuff into the washing machine, no? So this is the flushing delay that we call. So there's nothing going in, just the output is coming out. So it is causing some delay. Only in this middle steps, or if you have like more amount of steps in the middle, your pipelining actually becomes more and more efficient. So what do I come to say? So in that case, what should we essentially do? We have to try to increase the steps that's in the middle, right? So steps in that's the middle means you need to increase your number of people. So here we just have 4 people. So let's say we have more and more people. So if our n, so n is the number of people that you're considering, no? So let's say our n increases more. Okay, let's just take that condition. Okay, so Did you get the part of loading and flushing delay? Like there's over here, we are actually loading it. It takes 3 cycles, 3 people Okay. So I'll share my screen now. Okay, so what was I saying before? Was that so earlier we reached till after optimizing and making all of the stages equal. So we made all of the 30 minutes and we reached it to 2. Okay, 2 was our speed up. So why is it still not equal to 3? We need to know that there is some amount of delay that is there. Okay, so that is called as the loading and the flushing delay. Okay, so in this case, so we saw that it took 3 clock cycle to load, and then here there's 3 more clock cycles to flush, while there's not even like there's no input going inside, right? So only in your 4th clock cycle over here, so first 3 clock cycles over, and in your 4th cycle only you got your first output. So after 4th clock cycle, every time you're getting your output. So you're trying to optimize it, but there is some amount of delay that's there. So that is your loading and your flushing delay. Okay, so we can try to we can that is by actually increasing the number of people. So here it is just 1, 2, 3, and 4, like 4 people. So why can't we make it more and more people? So let's just consider that case. So where our n is very large. Okay, so let's just take our n to be 100 and k is still 3 because 3 is our number of steps. No, that is what we call it as latency. Okay, so the 3, which is our number of steps, that is called as latency. We have 3 steps, no, washing, drying, and the folding unit. Yeah. So our n is 100. So n, and it takes, and it's for 3 steps. So it's totally 300 steps that we have to complete. Okay. So, and always we consider in terms of time, no? So we consider the optimized, we'll just consider the optimized case where everything takes 30 minutes. Okay, so let's me just write it as minutes. Okay, so it's 300 into 30 minutes, which is actually 9,000. Okay, so let's consider for pipelining now. Okay, so for the number of clock cycles, it is n plus k minus 1, which is actually 100 plus 3 minus 1, 100 plus 2, which is 102, 100 plus 2, 102. And then we are multiplying with 30 minutes, which is 3060. So our speed up, it is always non-pipelining by pipelining. So it's 9000 by 3060, which is 2.94. So we are trying to reach 3 as n increases. So pipelining is essentially more optimized when we actually increase the number of people or the number of data that we're working on. Okay, so okay, here similarly what happens if we increase the number of stages k? Okay, so for that I'll just show you the example. Okay, so this is the example of 2-stage pipelining. So there is like fetch and execute. There are just 2 stages. Okay, so our k is 2 over here. So if you see this properly, you can understand. So fetch and execute, fetch and execute, fetch and execute. So okay, we can just see this whether the number of clock cycles. We know the formula, right? Number of clock cycles is equal to n plus k minus 1. So what is our n here? There are 3 instructions that is there. So n is 3, and then k is 2. There are 2 stages. K is 2 minus 1. 3 plus 2 minus 1, which is 4. 3 plus 2 minus 1 is 4, no? So there are 4 clock cycles. So you can understand in that terms. Okay. So I told you there is some amount of hardware that is required for pipelining process in itself, right? So earlier when we looked at one example, uh, when the execution unit, let's say it gets over in 40 minutes, and our instruction unit, let's say it gets over in 30 minutes. So this instruction unit has to wait for 10 more minutes until this 40-minute unit gets over, right? Then only it can be transferred to this. So that was our example that we looked over here, our 30-40 example. So in that case, we can have something called as buffer, so that you just transfer that data and then you wait for some time until this gets over. So this is the hardware that is essentially needed over here. Okay, so if you try to increase the number of stages, that is what our question is. So what happens if we try to increase the number of stages, which is k? So in that case, you have to increase the buffers also. So this is one stage. So instruction unit is one stage, execution unit is one stage. So if you increase your k, that is your number of stages, then you'll have to have that many amount of buffers also. Okay, so in case of this, when you see in terms of clock synchronization, you need to, it is very hard to synchronize like a large number of pipeline stages. Okay, so you need to make everything work properly. So what is the idea of pipelining is to make it better, like make it more optimized. You have to try and make the execution more faster. So if you're going to add more buffers and like reduce the clock synchronization, it defeats the whole purpose of what pipelining itself is. So that's why even like I think Intel's Pentium Pro or something, that itself they've tried till like some 21 to 30 clock cycles, 30 stages. So it can't like go more and more. Okay, so what happens if we increase the number of pipeline stages is that what happens to the clock synchronization? It reduces, and there are chances of more stalls. So you need to think about one question: how, like, what is the number of stages that we can go up to such that it doesn't decrease our clock synchronization? That is the whole point of how we start designing an architecture for how so that we can implement pipelining. So there are more stalls, so we'll discuss about what exactly stalls are. Okay, so let's just again go back to our very old example now. Okay, we're done with this. Sorry. Okay, so now let's just look into all of these points now. So pipelining doesn't help latency of the single task. It helps throughput of the entire workload. So what do I mean by this point is, so the latency is the number of steps. So whatever condition that you did till now, that is like you still had to perform all of these three tasks. Okay, you're not like individually trying to improvise any tasks. Like you have to still complete those tasks, right? So you have to complete these stages. There are still three stages. You're not trying to reduce the three stages into two stages or one stage. There are three stages in every single condition that we checked. So initially non-pipelining also you had three stages, and then when you made it into a pipelining also you had three stages. Then after optimization also making it all 30 also you had three stages. So the number of stages and all doesn't change, but your throughput changes, as in you tend to get your output faster and you try to optimize in terms of your time. So you reduce the time of your entire cycle, so you get your output much more faster. So your throughput or your output, like it comes much more faster. Okay, so that is the first point. Then the second point is the pipeline rate limited by the slowest pipelining stage. So what do they mean here is, so let's just again take this example. So here the first one takes 30 minutes, second takes 40, and the third takes 40. So if you see here, and I again told you, right? So if this is just happening and this gets completed, you need to wait for some time. So this step is what is deciding our entire pipelining time. So our pipelining time is defined by the slowest step in the cycle. So this 40, even here it is 40. Let's say if this is the highest time that is taking, so that will become the slowest stage in our pipelining. So that will be the slowest step, and based on that only that is like our worst case, like how we deal with data structures. So yeah. So, and then multiple tasks operating simultaneously using different resources. So that is what the first point that I said regarding what pipelining is. So multiple tasks happening at the same time. So different tasks happening at the same time. That is what pipelining is. And potential speed up is proportional to the number of stages. We saw the whole NT, everything in terms of that. So why it was, we just saw that. And then unbalanced length of pipelining stages reduces the speed up. That means we saw the second condition, no, when it was just normal pipelining condition, but it was still two. No, sorry. It was normal pipeline condition. It was 1.75. Only after we made it all 30, it became 2. It became slightly more optimized. So that means if it is unbalanced length, so if each of these steps take unbalanced amount of time, then our speed up reduces. So unbalanced length of pipelining stages reduces the speed up. And then time to fill pipeline and time to drain it reduces the speed up. So I showed you the example of loading and the flushing delay, right? So that time to fill the pipeline and drain the pipeline also reduces the speed up. Okay, this stall for dependencies is our next part that we'll be looking into. That's essentially like when you are actually running your program or you're just running something, there are some unexpected circumstances that you might have to encounter. So how do you how do you actually deal with it, and how do you try to get rid of it, though it cannot be like completely get rid of? What stall for pipelining is. Okay, so in case of this example, if you're trying to wash the clothes and your pipelining, as in your detergent powder runs out, or when you're trying to like fold clothes and iron your clothes, your current goes off, something like that. Just I'm giving some random example, but yeah. So that is the unforeseen circumstances that you might have to encounter. So you can't really control it, right? So what can you actually do to control it, or what is actually done in terms of like computer perspective? That is what you're going to see later in like some time. So before that, okay. So now I showed you an example of two-stage pipelining, right? So fetch and the execution unit. So this was the example that I showed, and we have buffers inside. So now a four-stage pipelining. So fetch, decode, execute, and write. Okay, so if you see this, again we can calculate the clock cycle. So it's n plus k minus 1. So our n is 4. N is 4. K is also 4. So 4 plus 4 minus 1, which is 7. Okay, so 7 is our clock cycles. So yeah, so as you increase your number of stages, you need to increase your number of buffers also, right? So you should somehow reach at a limit where, and you should ensure that the number of pipelining stages should itself not like defeat the purpose of pipelining. Okay, so that is what we looked at before. Why can we not like increase k so much? Okay, so now role of cache memory. Okay, before that, okay, this fetch, decode, execute, and write. So there are four stages, right? So in this four stages, what do you think could be the slowest stage? So if I had to tell, it will be your fetch and your write unit, because fetch now you're actually trying to access it from the memory, and then write, you're writing it back to the memory. So it involves some amount of memory that you need to access from the memory. Okay, so in that case, that might become slower. That's why we have something called as cache, right? So that's what we learned like earlier also. So we have something for cache to ensure that things gets accessed faster. So that is why we need cache that's saving us from so many problems. So this whole story that is talking about is essentially what I said. So each pipeline stage is expected to complete in one clock cycle. The clock period should be long enough to let the slowest pipeline stage to complete. So I told you that the slowest stage actually decides the entire time of the pipeline stage itself. No, so if the clock period is long enough, we need to make the clock period long enough so that the slowest pipeline stage also gets completed. So we studied in DD, right? So our clock cycle, as in the clock cycle, which is like a square wave, you need to make the high so long enough so that even you need to wait for long enough so that the slowest pipelining stage also gets completed. Okay. So you just make this high long enough such that you make sure that even the slowest steps gets completed. Okay, that is what this point is talking about. Then faster stages can only wait for the slowest ones to complete. We did see that, no, the faster stages, it just waits for the slower stages to complete. So sometimes accessing from the main memory is very slow, right? So in that case, we have something called as cache, because if you need to access from the main memory, that itself is a very, very slow process. Okay, so it will eventually defeat the purpose of pipelining itself. So if that stage, so I told you that the slower stage will decide the speed of your pipelining. This may accessing from the main memory will be the slow stage. So if it is very, very slow, then it is going to defeat the purpose of pipelining. So pipelining will become almost useless, right? So that's why we have cache. Okay, so in if you have cache, so that you access things faster. So now the potential increase in performance resulting from pipeline is proportional to the number of stages. Okay, a very random point. So it's the same point that we talked about. The speed up is proportional to the number of pipeline stages. Okay, so this increase would be achieved only if the pipeline stages require the same time to complete. So I told we did discuss the point where we made all of the stage equal time. No, we made all of it from 20, 30, 40 to we made it to 30, 30, 30 each. So our speed up increases in that case, and if there is no interruption in the whole program. But that doesn't always happen. Okay, so we might encounter some interruption no matter what. Okay, so what are those interruption? What do we actually call them? How does it actually work? Is what we're going to look at now. Sorry. Okay, did everyone get till now? Get everything till now? Okay. Okay, so we just looked into what pipelining is. So why do we essentially need pipelining? In the example that we saw, what are the ways we can use to optimize the pipelining? We first made the time periods equal. We then increased our n so that it becomes almost equal to the number of pipeline stages. The speed up becomes equal to the, not proportional to the number of pipeline stages. So it can't be completely equal because of the loading and the flushing delay. Then we just now are going to start with what stalls are and what are the hazards of pipelining. So 1 second. Okay, so let's just look at this now. Now if you see here, earlier when we saw the four stage pipelining, it got over in some 7 clock cycles, right? So we did 4 plus 4 minus 1, which was 7 clock cycles. So now if you see here, it takes 9 clock cycles now. So what is causing this delay? So there's a delay in your execution stage E2 in your second instruction. So this delay, and eventually there are more delays that is causing the pipeline stage to become even more, it takes more time. Okay, it takes more amount of clock cycles. Okay, so from 7 it has become to 9 because of this stalling. So we just call this as stalling or bubbles or something. Okay, so let me ask something. So here, why do we not have the execution stage here? Okay, this E2, it's getting delayed. Okay, fine. But why do we not have E3 also here? Why is this E3 also getting influenced by the E2? Like, why can't we just have the execution 3 unit over here in itself? Would anyone wants to give it a try? If I had to give a clue, it just connects to the original definition of what pipelining is, which I gave, like, first I gave that only. Okay, so I'll just tell that. So basically, what did I tell? So pipelining is actually two different instructions happening at the same time. So if this E3 just comes below E2, that means your two execution stages are happening in the same clock cycle. that is not what pipelining is. It is actually superscalar, whatever, superscalar execution. So that becomes parallel if you try to make everything happen at the same time. As in everything, as in the same kind of instruction happening at the same time. So if you try to make execution E2 and E3 happening at the same time, then it is not pipelining. So just like the understanding that I wanted to tell. Okay, so in terms of pipelining, there are pipelining. Previous pipelining is said to have stalled for 2 clock cycles. I said no. Earlier it was 7. Now it has become to 9. So there is a stall of 2 clock cycles. So any condition that causes a pipeline to stall is called a hazard. Okay, so there are 3 types of hazards. So the first is data hazard, then instruction or control hazard, then the structural hazard. Okay, so this data hazard is actually when like there is no any condition in which either the source or the destination operands of the instructions are not available at the time of the expected in the pipeline. So I'll just show you examples, but what it essentially says that when you are essentially expecting for some data but that is not available, or it's available but it's not the right data, it is not the updated value, like, so your logic of the program itself goes wrong, right? So then in terms of instruction hazard, a delay in the availability of an instruction causes the pipeline. So if you don't even have an instruction, then that becomes an instruction hazard. Okay, this is just some definitions, you can understand it easily with examples. So now structural hazard, the situation when two instructions require the use of same given hardware at the same time. So for this, if I had to give an example, this, okay, let's say you have your fetching and your writing units. If it is trying to access the same memory, you are trying to at the same time, you are trying to fetch something at the same time as well as write it on the same time. So which will be given more priority or something. So you can't do that, no, you can't just decide on that, right? So that is like a type of structural hazard. So two different there are two different instructions, that is fetch and write happening at the same time, but it is actually trying to access the same hardware, that is the memory. Okay, so in that time there will be the structural hazard. Okay, so nowadays there are like multi-port memories, so this is not really a problem. So this is just an example of what structural hazard is, but it's not like a real-time problem nowadays. So yeah, so now we will. How long is the meeting there? Okay, we will now go on to. Okay, this is just a small example of instruction hazard. So over here, so if we'll look into more instruction hazard in detail, but I'll just explain what is here now. So there are 4 stages: fetch, decode, execute, and write. Now in your instruction 2, your fetch unit is taking a long time. So when might it take long time? So when it's fetching from something, so it's fetching from, say, cache. So it is trying to fetch from the cache, and there is a cache miss, as in it is not found in the cache. That means it will then go to the memory and then try to search in the memory and then fetch that unit, right? So is causing that is causing like a stall here. So that is why this fetch unit, I mean, I'm just giving an example when the fetch unit can actually cause a delay, right? So let's say when there's a cache miss, when the data that you're trying to find, that you're trying to fetch is not in the cache, so you need to go to the memory. So there is some delay, that always accessing from the main memory is always causes some delay, no? So that is why the fetch unit has some delay. So, and then eventually everything else will also have a delay, right? So here I think instead of finishing in 6 clock cycles, it is getting over in 9 clock cycles. Okay, so there are 3 instructions and 4 stages, so it should have happened in 6 clock cycles. Now because of the delay, it's delaying it to 9 clock cycles. And then, okay, here the stalls or the idle periods is what they called as bubbles. That's all. Okay, so now if you had to look into this now, what does this example say? Load x r1 comma r2. Okay, so first, so what will you essentially do? You're actually like from r2 you're loading it to r1, whatever the data in the r2 register, you're loading it to the r1 register. Okay, so first what you have to do, so what will r1 r2 do first? It has to access r2's data from the memory, no, like from the memory, what the r2 data, whatever is it, it has to be accessed and then it has to be stored into the r2, and then it has to be returned into the r1. So after r2 getting access from the memory, that value is getting returned, r return is written, yeah, it is writing into the r1. Okay, so yeah, now let's just, that is the explanation for the load thing. Okay, now let's look into here what is causing the stall or the delay. Okay, so now load, I told you this R2 is actually involving the memory condition. So here the execution stage itself, they're dividing into memory also. In 5-stage pipelining, you will actually have memory as one more stage in your pipelining. Okay, so in your load, so first you're looking into memory. Okay, so because first you need to actually, this R2, it is getting fetched from the memory. Okay, so it has to be fetched from the memory and it has to be returned into the R2. Then only can you write your R2 value in your R1. So what I'm going to say is, let's just take this M2 and W2. Okay, so let's just, sorry. So let's just take M2 and W2. Okay, so if you see here, first for R2, so this is our load instruction. So first, let's say for our R2, it has to be loaded to the memory and then return into the R2, right? So whatever the value is from the memory, it has to be returned into the R2. So then only can you execute the write stage. Then only can R1 be equal to R2, as in you're loading, no? So then only this stage can happen. That's why there is a stall here. If you see here, there is a stall over here. If you put this over here, if you can't really put this writing condition here, because by that time, what will happen? Let's say if you have W3 over here, then you're actually trying to write at the R2 and also trying to write at the R1 at the same time. There might be some data inconsistency over there. Okay, so that's why you'll have to stall this and you have to ensure that R2 is fetched from the memory and returned into R2. The value which is fetched from the memory is returned into R2. Then only can you actually move or like load your R2 into R1. So a writing condition can happen. That is the that is an example of structural hazard. Okay, so you're trying to access the same memory at the same time, that you can't do. So that's why you're having a stall over here. Is this clear or was it slightly confusing? Do you want me to repeat anything? Is it clear? Anybody wants me to repeat? Okay. Okay, so yeah. Now again, pipelining does not result. Sorry. Okay, pipelining does not result in the individual instruction being fast. I think it's the same thing. No, okay. So pipelining does not result in individual instructions being faster. Rather, the throughput increases. We've already seen this. throughput is measured by the rate at which instruction execution is completed. It's just a definition. Whatever we have looked into before, that's the same thing. And then pipelining stall causes degradation in pipelining performance. So the stalls that we discussed before, so the stall over here in our previous example, it actually causes a degradation in our pipelining performance. So we have to try and identify all the hazards and try to minimize it in some way. So that is our whole motivation also, because we are trying to optimize it. But if the stalls is going to make it so bad that pipelining itself becomes useful, then you can't really do much, no? So you have to try and identify the hazards and try to minimize the impact. Okay, so now we'll look into wait, can you hear me? Okay, there are only 6 minutes more. Okay, fine. So we are actually going to look into data hazards and instruction hazards and like go into the details. Okay, so let me just share. Okay, so I'll just go through the PPT of. Can you see my screen with the PPT? Okay. So yeah. So pipelining improves the system performance in terms of throughput. We've already looked into it. We'll just brush it up once. Faster circuit technology, and then more than one operation performed at the same time. That is what pipelining is. And then we looked into all of these examples, all of the cases, everything that we looked into. And then two-stage. This is two-stage pipelining that we looked into. Now, if there is four stages, then there is fetch, decode, execute, and write stages. That is our four-stage pipelining, which took us 7 clock cycles. Then you have to have buffers. And we saw the role of cache memory, where accessing has to become faster because main memory is very slow. If you try to access everything from the main memory, then pipelining itself becomes useless. Then we saw about stalls, like what exactly is stalls. We didn't go into details of it yet. So what exactly is a stall? So what could be the reasons why stalling can happen? And then the types of stalls, data hazard, control hazard, and structural hazard. Structural hazard is when you're trying to access like the same memory at the same time by two different instructions. So instruction hazard, we just saw pipelining stall caused by cache miss in F2. So there was a cache miss, so it took a long time so that it went and fetched it from the memory. So that's why the stall happened. Then these are the idle periods. The stalls are called as bubbles. Then for structural hazard, R2 we had to put it in R1. So that means it there is trying to access at the same time. So access the memory at the same time. So there is some amount of stall that you have to do to optimize it. So you can't really have two instructions at the same time. So that's why. Then we just looked into all of these points now. Now we'll move on to data hazards. Okay. So this data hazards, what exactly is it? So I told you data hazards means you're not essentially having the data that you might need for your program execution. So let's just consider this. So A is equal to 3 plus A. So this will essentially be in your decoding stage. Okay, I'm sorry. 1 second. Okay, I think it's gonna end in 3 minutes now. So I'll probably like start like a new meeting and then Is that fine? Work. Okay, I'll share my screen now. Till now, is everything clear? Do you want me to repeat any part? Okay. Okay. So let's just move on to data hazards. From now, it's just all very simple stuff. Need not break our heads. Just understanding of what pipelining is should requires like a time. Okay. So now data hazards. Okay. So this, let's say these two instructions are there. So a is equal to 3 plus a. So that is essentially decoding, no? So that is our decoding stage. And then b is equal to 4 into a. Okay, so b is equal to 4 into a. So that means you need the previous a's value so that you calculate b. So you need to have the updated a value so that you calculate b. So this is actually your fetching stage. Yes, I'm not able to do. Okay, this is your fetching stage. Okay, so over here, okay, let's just go to our previous example of our fourth stage pipelining. Okay, so if you see there, okay, it's here. So if you see there, the decoding and the fetching is happening at the same time. So if that happens at the same time, that means you can encounter some kind of data inconsistency. So the decoding stage, what was the first instruction? It was a is equal to 3 plus a. So the decoding stage, and then b is equal to 4a, 4 into a. Okay, so yeah, if you see here, the decoding stage and your fetching stage. Okay, so that was 3a is equal to 3 plus a, no? So that was our decoding stage. And then our fetching stage was b is equal to 4 into a. Right? So if both of this is going to happen at the same time, then there might be some inconsistency that might happen. So our A sometimes need not be the updated. Like let's say our A is 5 initially. That means after this it should become 8. So we need the 8 value and B to be 32. But if this A is not updated by some chance, this it doesn't become 8. So we'll have our initial value of A. So we'll have like 4 into 5, 20 as the answer. So some data inconsistency might occur, right? So this is one example of data hazard. So what we can do, we can have some intermediate variables, say C. So with that, we can actually try to avoid this hazard. So we are just trying to avoid hazards now. We have to try to minimize the effect of the hazard. So A is equal to 5 into C, B is equal to 20 plus C. So in this case, if you see, there is no inconsistency as such. The second statement is not dependent on the first statement. Over here, the second statement was dependent on the first statement. So you need this first decoding stage to complete, and then only you need the fetch to be done. But in our pipelining, both of this happens at the same time. See, we need to do pipelining. We need to ensure this decode and fetch when it happens at the same time. But still, if this kind of clash occur, we need to also have a case for it, right? So yeah, when two operations depend on each other, they might be executed sequentially in correct order. And then again the same similar example. So this R4 is our destination and R6 are the destination. The first two are our source. So R2 plus is actually R2 into R3. It's wrong here. It's multiplication. So R2 into R3, it's getting stored in R4. So we need R4 in our second thing. So R5 plus R4 equal to R6. So this R4, we need it over here, right? So it's getting dependent. So there might be some inconsistency that might happen. So if you see here, so essentially this is in our decoding stage. We are decoding. Okay, let's say D2. Here we are actually calculating it and then writing it, correct? So we are fetching it and then writing it to R6, right? So if you see that, over here, so D2. So what's happening here? So in terms when it comes to D, no. I'm 1 second. No, I think. Okay, so what essentially, okay, leave this part. So what essentially is happening here is at W1, so this R2 and R3, it gets executed and then it gets multiplied and then it is getting returned to the R4. So that is our writing case, okay, in terms of multiplication. So in this decoding stage, while it is actually decoding, so this R5 and R4, this is the decoding stage, the D2 case. Okay, so this is decoding. While decoding, it is noticing that it needs R4. Okay, but R4, it is still not returned in that. So next is, see, this W1 is only writing this R4 part, no? That did we all get it? Okay, so this is your executing this R2 plus R3 are doing, and then you are writing it to the R4. That is your W1 case. So now the add condition, add is a I2 instruction. So when you're decoding R4 plus R5, that is your D2 case. You're now noticing that you need R4 from somewhere. But when the time you're doing this D2, you're still not writing something to R4. In your next clock cycle only, you're writing R4 with W1 instruction. You're writing your R4. So R4 only gets updated in your next step. So when you're decoding, when you need this R4 over here, you will get your previous value and not the updated value. So hence you need to stall for some time and then only you will have to do your D2. Okay, so you need to stall for some time and then you have to perform your decoding stage and then you can continue. Did everyone get this point or was it confusing? Anyone wants me to repeat? I can repeat it once. Okay, so this part, so what I'm essentially saying is this R4 you're writing into R4, that is a W1 case. So you're decoding R4 plus R5, you're storing into R6. Okay, so for that you need R4. So R4 is not yet returned. It is getting returned in the next cycle only. So you need to delay your decoding stage. So that's why you're having the stall over here. So this is an example of data hazard. Okay, now operand forwarding. So now what can you actually do? So instead of so now there is like some inconsistency that's happening here, no? So what can you do? Okay, here we are trying to stall. So that is one condition that you can do. So if you try to stall it, then in the next step you can start continuing and then it goes on. Normal pipelining continues after you're stalling. So is there any other way that you can do it? Okay, so that's when operand forwarding comes. Instead of from the register file, the second instruction can get data directly from the output of ALU after the previous instruction is completed. So what it is essentially saying is this R4, instead of getting stored into the R4 itself, instead of getting stored into the R4, can directly get sent to this statement so that this gets executed. So I'll just show you the diagram over here. So this is the entire structure of the whole hardware. Okay, so usually what happens, usually you have the two statements, right? So if you see here, multiply R2, R3, R4, so these two gets multiplied and gets sent to R4. That is your register file. Okay, then this R5 and R4, it gets added and it gets sent to the R6. So usually when there are two sources, first you get multiplied and you get sent to the ALU. ALU multiplies and the result is sent and it goes to the register file, which is R4. So our first multiplication case where R1 and R2 is added and sent to R4. Okay, so this is how it usually happens. So now in your next statement, when add comes, that time, instead of doing that, what can you do is you send both the datas over here, the ALU and the result, and it gets sent over here back, so that you need not go through this process of sending it to the register and the data inconsistency happening. Okay, so instead you can just send it back again. So R2 plus R2 into R4, R2 into R3, that gets sent to over here, so that this both gets added and then it returns to R6. Okay, that is what operand forwarding is. So in case of data hazards, what you can do is first stall. That could be one possibility that you can do. Then operand forwarding. And then another thing is, okay, now let's just again consider this example. Okay, this NOP is something called as no operation. So what did we do before? We actually stalled it, no? So instead of stalling it, we are just not doing any operation. It's like a dummy operation, okay? You're not doing anything. Say in Python and all, there's something called as pass, no? So it doesn't do anything. So in our statements here, so this NOP also takes one clock cycle, no? If considering every instruction takes one clock cycle, this also takes one clock cycle. So it is similar to stalling, but just you're ensuring no operation takes place, so that this add operation gets enough time so that this R4 is updated. Okay. Okay, so in case of data hazards, there are three methods that you can follow. There's stalling, operand forwarding, or you can use the no operation or dummy operations. So yeah, is data hazards part clear? Okay. Okay, next is something called as side hazards, side effects. So what is that? So sometimes an instruction changes the contents of a register other than the one named as the destination. So let's just say, like, okay, there are something called as conditional flags, no? So these conditional flags, uh, sometimes you need to wait for that also to happen. Okay, so how do I put this? Mm, 1 second, like other than one named as the destination. So when a location other than one explicitly named in an instruction is affected, the instruction is said to have a side effect. Okay, 1 second. I have no idea what this is. What does this say? Sometimes an instruction changes the contents of a register. Okay, I'll just look into what this is and come back again. Okay, this part alone I'll look into and come back. So yeah, now let's go on to instruction hazards. So instruction hazards when can it happen? So I told you when there's no instruction that is there. Okay. So we just looked into an example where our F2 got delayed so much because of cache miss. And that's why it had to go and get it from the memory. And that's why the stalling happened. And then branching statements. So branching are the loop statements. So that time, how can instruction hazards actually happen? Okay. So over here, okay, let's say there's a branch condition. So branching condition, so this is like a two-stage pipelining, no? Fetch and execute. So it will notice that it is a branch condition only in E2 condition. Like when it is executing, it will notice that I2 is a branch condition. So from I2, you have to jump somewhere. Right. So that is what branching means, no? So in your execution stage, it will see loop is there. So you need to actually jump to somewhere else. Like that, it will notice. So by the time E2 is getting noticed, like E2 is noticing the loop or the branch statement, F3 or the fetch statement would have already been completed, right? So if you need to jump from I2 from so in your branch condition, so essentially you're not going to jump to the next statement, no? So you're going to jump to some n, like some n plus n statements. Okay, you're going to jump some amount of statements. So by that time, this F3 is already fetched. Okay, that data is already fetched. So you have to like remove this data, and then you have to again go to that instruction. So let's say you're going to this instruction. So then you have to again fetch it for this and then execute. So this is how it should work, no? So if there are like more number of stages, that means you need to clear everything out. Then only you have to go to the jump, right? So this causes some amount of delay in your whole process. You need to refresh everything that you have fetched, and then you have to go again and fetch something else. So that happens in terms of loop conditions or your branch statements. When you're jumping from one statement to other. So this is what I said. So let's say your branch condition. So here there are 4-stage pipelining. No. So your branch condition is computed in the execution stage. So let's say your branch condition, it's computed in the execution stage. So it will tell I have to jump from this statement to this statement. So let's say we are jumping to maybe this statement. Okay. So that time, so by the time this execution A2 gets executed, these 3 other statements also gets executed, right? So in this case, you need to flush out all of this, all of the data that you have till here. You need to flush out, and then you have to go to this statement and then fetch, decode, execute. Right? Then it follows the same. Okay, so this is like what instruction hazard itself is. Okay, in terms of branch condition. Is this part clear till now? Okay. So next, so if you see here you need to actually in 2-stage pipelining, you need to just flush out this only the F3. But here in 4th stage, you need to flush out this fetch, decode, and then this fetch. So as soon as your number of stages increases, you need to flush out more and more when you're doing branch statements. So this is also one thing we earlier discussed. No, why can't we just increase k to so much? Like why not? That means your speed up is proportional to k. Now your speed up becomes infinity if you make k infinity. You really can't do that because because branch statement is very very like a very common part in terms of programming. No, so if you need to jump to some statements, you can't keep flushing out like infinite minus one statements all the time. Correct. So that is also one point as to why you can't like increase k to infinity or like, k to a bigger number. Okay, so here again the same example, branch computed in the decoding stage. So they see that the branch is in the decoding stage. So you need to flush out this F3 part, and then only you can jump to some other stage. Okay. So next we are going to look into how we can solve instruction hazard. Okay. So in that case, this instruction queue and prefetching, that is one way where you can solve your instruction hazard. So let's just consider one example maybe. So let's say you have the following data in your cache. Okay, so maybe you have it from, one second, you wait. Okay, so let's say in your cache you have data from A1, A2, A3, A4, A5, just some numbers you have. Okay, so let's say you have all of this in your cache. Now first you are trying to access A1, so you have it in your cache, so it's fine, well and good. Then you're trying to access A2, it's there in the cache, well and good. So when you're trying to access A1 itself, the cache will actually take everything and keep it in the cache. Like it'll take A1, A2, A3, it'll try to take as much as possible, thinking that you might need the other things later, like you might ask for the other things later. So that's how cache works, right? So you have to, it accesses everything in advance and then it keeps like that. So A1, A2, like that. Okay, so let's say now it is asking for A8 or something. It's not really in the cache. So then there is a cache miss. So it goes to the memory and then it fetches it. So here it goes through fully. So by the time it goes through fully, and by the time it goes to the memory and takes and comes, so it almost might match. Okay, so let's say you have like a lot of things in your cache already, so it will run through everything. That might be similar time to how A8 is getting access from the main memory. Okay, this is what the concept of instruction queue and prefetching is. So you try to queue as much as possible, so that, and then prefetch and keep everything possible, so that you won't really find the delay. So you can use all of this, and then by the time you reach A8, you will also get A8. You might prefetch and keep A8 by the time all of this occurs. Okay, so let's look at, okay, so let's look at this now. I think okay, I'm so sorry. I forgot to tell something in data hazards. So we looked into this example, right? So we looked into this multiplication and addition example, right? So what this is just essentially a raw hazard, RAW hazard. So raw hazard means wait, sorry. Okay, so basically data hazards are, this example is raw hazard. There are three types of hazards. Okay, so under data hazards, so raw hazard, war hazard, WAR, and WAW hazard. So raw hazard is what we discussed now. War and wow, it is not really common in pipelining. It is very common. It's common in superscalar execution. So probably we'll deal with that later. So yeah, I just wanted to tell that this is an example of raw hazard, which is read after write hazard. So yeah, now jumping back to instruction queue. Okay, so branch timing with execute instruction queue. So what is happening here? So branch timing is in the presence of an instruction queue. Branch target address is computed in the decoding stage. So again, they identified the branch in the decoding stage, which is D5. As in, they say that it is a branch statement, and then decoding says they are computing that it is a branch. So by then, it has to flush out all of this. That's all. That's what it says. So what can you do to avoid this? Is something called as branch folding. So I'll just try to explain branch folding through a very, very simple analogy or something. like maybe we can just take like a traffic signal example. Okay, so say you're driving, so and then you suddenly encounter the signal. Okay, so then what do you do normally? You just stop, you just see what size signal it is, and then decide whether then you see, maybe if it is green and then that left and right symbol is there, you try to go left or right depending on that. Okay, and then in let's say a condition where the branch when the signpost itself is like removed. Okay, let's say that left and right thing itself is removed, so you don't really stop at anything, right? You just directly go into whatever path that you wanted to go. Okay, so you are actually trying to avoid that branch itself. So how do I tell it in terms of this is, you actually prefetch and keep the branch itself before. So I told you about prefetching, no? So if you need to jump from A5 to A7 by skipping A6, the by free prefetching, you're actually reading everything in advance, and you're actually trying to fetch everything in advance and keep, so that you don't really notice that branch exists. So you no need to flush everything out and all of those sorts. So you don't. So by then this F6 wouldn't have been done. So you just from if you encounter this D5, you encounter branch, and if you need to jump, you just jump off. This F3 wouldn't have happened by then. So that is what branch folding is. You just as you encounter branch and you prefetch it, you have to, while prefetching, your cache should be such a way that after D5 it should go to this fetch unit of this statement F of k, like some kth statement. Okay, so that time you wouldn't have actually just fetched this sixth instruction. So that is what branch folding is. So at least one instruction is available in the queue other than the branch instruction. Okay, so this conditional branches. So conditional branches, we have actually seen it earlier, right? So what is conditional branches? You have all of those conditions. So jump if carry, jump no carry, this if it is a zero or not, all of the flags that we have. So in that case, you need to wait and see whether this is giving 0 or 1, and then only you decide whether to go inside the loop or not go inside the loop. So there is some amount of waiting period, the dependency that is there. So in data hazard also we saw that dependency caused the hazard. So here also, in case of conditional branches, the dependency is what causes the branches. Okay, so then there's something called as delayed branch. I'll explain it with the example over here. Okay, so if you see delayed branch, so our original thing is, so shift left R1, decrement R2, and then branch. If branch is 0, then loop. So it's telling decrement R2, now you're decrementing R2. So if the R2 becomes 0, then you go back to the loop. If it is not, now you go back to the next statement. Right? So this is what it tells. So here we are trying to reorder in such a way that there is some instruction that happens after the loop. Okay, so decrement R2 branch equals 0 and then loop. So as the R2 becomes 0, it goes on to the loop. Okay, so here there is no amount of waiting period, whether or not, here if you see there is some amount of waiting period, so it has to depend on the R2, and then it goes, it either goes to here or it goes to the next. So here is the waiting period. This third statement is the waiting period, or the delay slot here as we call. But if you see this example, the waiting period is over here. So again the same thing, R2 becomes 0, it will decide it will whether to go to the, if it is 0, then it will go to the loop again and it will run again. If it is not 0, then it again comes to this. Okay, so there is some statement that actually gets executed whether or not this is getting delayed or not. But over here it is a condition between loop or next. Over here this gets executed no matter what. So by reordering statements, we can ensure that the delay is getting reduced. So if you see here, first decrement, then branch, then shift. So if we encounter a delay slot, so if you encounter a delay slot, then a branch is taken. So again that goes back to the branch as in the loop. So branch is taken, and then there's a branch, and then there is a shift that is, and when the delay branch is not taken, okay, so in this shifter, if the delay branch is not taken, it goes to the add statement. Okay, that is what it's talking about. If it is the delay branch is not taken, it is going to the add statement. So if you see here, first in that diagram what they talked about was when the delayed branch is taken. So the delayed branch is this third statement. So if that is taken, that means it goes back to the loop. If it is not taken, it goes back to the add. So that is what talks. If it takes the branch is taken, it again goes back to the loop and perform the same statements. If it is not taken, it goes back to the add. So there's something called as branch prediction. Okay, what is so essentially this concept of randomization. Okay, so I told you right in the cache example that I explained. So this cache, what randomization techniques the computer nowadays uses is, like, let's say first branch, it will just use like a randomization technique. So let's say first branch, you just assume saying first branch will be taken and the second branch will not be taken, then third branch will be taken and the fourth branch will not be taken. Like, let's say your randomization condition is, alternatively you just assume things that branch will be taken and branch will not be taken. So in that case, more or less whatever you try, it might mostly get succeeded. Okay, so see, even I had a doubt saying there is a chance that it goes completely opposite from the prediction, but apparently, like, this randomization technique is something that is like very common in computer science, and is actually, there's something called as LRU algorithm, okay, that we'll deal with in memory chapter. So that time, like, I'll probably like elaborate more on this. But this randomization technique is something that makes this branching prediction. So you're trying to make a prediction saying whether this branch will be accepted or not. So that prediction more or less tries to become equal, and it is actually very much efficient also. Okay, so yeah, this is what delayed branch is and branch prediction is. So then better performance can be achieved if we arrange for some branch instruction to be predicted as taken and others are not taken. So you assume that some branches are taken and some branches are not taken. You predict it, and then based on that, you use the hardware to observe whether the target address is lower or higher than the branch instruction. And then you let the compiler actually include the prediction bit. So this comes under the LRU algorithm also. So in that time, we'll go in like much more detail about it. Okay, so the superscalar execution, we'll deal with it in like the next session that we'll be doing. So it's basically just parallel processing, not much. So we'll just like 5 minutes, we'll just complete the theory part of it and we'll move on to the questions. Okay, so this formula we already know, right? The T is equal to NS by R, where S is an average number of clock cycles and R is the clock rate, T is execution time, N is the instruction count, all of those. Okay, so this and all we already know that. So now we actually looked into the case. The end stage pipelining has, okay, there here we actually took K as stage pipeline. We took K stage pipelining. Here, what the example that we took, it was K, right? K was the number of stages. We were talking about if you, how much can you increase your K? Like if you speed up is actually proportional to your K, no? So how much can you actually increase? So you can't increase by so much, right? So that is what we are dealing with over here. So here instead of N, just consider K, like how we have discussed. Okay. So how much potential increase in instruction throughput can be realized in practice? So what is the good value of K is our question. How much can we increase? We can't just keep our K to be 10,000, have 10,000 stages, right? So we have just already discussed about it. We should have the number of stages in such a way that it doesn't defeat the whole purpose of pipelining. So we need to consider the hardware also. You need to consider the number of buffers. You need to consider the clock synchronization. Everything you need to consider in this case. So as the number of stages increases, the probability of pipelining being stalled also increases. So when you're branching, so all of that we discussed till now, that is what the answer to this question essentially is. So if you see here, just a small thing that we already discussed. So here, the non-pipelining case, where Tn is your non-pipelining timer. So it actually, for n task, it takes n into Tn. And then for your pipelining, we already saw if Tp is the time of the pipelining condition, then this number of clock cycles into Tp. That is what we also saw, no? So speed up is actually this by this n into Tn by k plus n minus 1 into Tp, right? So the example that we already saw, that's all. We just introduced R, but here is just formulas, N, T, P, K, everything given. So yeah. Now, just the same example. So if TP is 20, and then you have 4K is equal to 4 and N is equal to 100, you just substitute in this formula and then you will get your answer. So in your pipelining, it is K plus N minus 1 into TP. So TP is 20, as I said. K is 4 plus 100 minus 1. So 103 into 20, which is this. And non-pipelining, it is Nk into Tp. So N is 100, K is 4, 100 into 4 into 20, this. And then speed up is non-pipelining by pipelining. So you get it 3.88. So which is almost closer to 4. 4 is our K, right? So it is almost equal to 4. So yeah. This is what I wanted to say. Is everything clear till now? Is everything fine? Okay, so now we'll be moving on to questions. So I think I'll share like a new link because we have only 23 seconds left. Okay. So I think I'll hand it over to Naga Dharsan now. I'll share a new link. Thank you so much for joining. Thank you.